Hello, class. This is Mrs. Oppold, and we're going to take a look at Section 4.2 today, especially for the students that were gone on the field trip. So I'd like to walk through with you a way or a method that we're going to work on how to approximate the area of any plane region, meaning any two-dimensional area. So we're going to look at left-hand and right-hand approximations today. It is known as the method of Riemann sums. And then tomorrow, when you're back with us, hopefully you can follow along with midpoint and trapezoid method. So taking a look at the pictures down here, you can see what we're trying to achieve. We're going to try and draw in rectangles to fit under our curve, or perhaps rectangles that extend beyond our curve, and use those rectangles to sum up the area under the curve, because we know how to calculate the area of a rectangle, length times width. It's quite easy. So if you notice here, this rectangle is under the curve. We could also call this, since its one end point is lying on the curve, this is an inscribed situation, or the rectangles are inscribed. That will fit over here. I would call that the sum of areas of the inscribed rectangles. This is known as a lower sum method. So the lower sum. That must mean then that these are circumscribed rectangles, which they are. And we notice that if I look at this and I were to add up all the area from these rectangles all the way down to the x-axis, this would overestimate my area, and thus it's called the upper sum, because we're going to have more area than what truly lies underneath that curve and above the x-axis. So that's kind of the idea. One thing I want you to think about is just a regular equation. Say I have some object moving at a constant rate of 3 feet per second. We know that rate times time equals distance. So if I'm moving at 3 feet per second and I multiply it by some amount time, I would get the distance traveled, right? We've been calculating that for a very long time. But have you ever considered it in a graphic form? If we were to use our y-axis as the velocity and place time on the x-axis as our independent variable, and I graphed time versus velocity, it might be kind of interesting. We were traveling at a constant velocity or constant speed of 3 feet per second. That becomes just a nice horizontal line. For any particular time, I could calculate out real easily 3 times 1, that I went 3 seconds. That turned out really nice, didn't it? That I went 3 feet. Well, if you take a look at the area represented here, I'd have a width of 1 and a height of 3. That turns out to be 3. What would happen if I traveled for 4 seconds? Going 3 miles or 3 feet per second, I would have an area of 12 feet. So we can really use area under the curve to help analyze and calculate certain functions. So here's what we're working on. If, say, the velocity is not constant, which is, quite possible, we might guess that the distance traveled is still equal to the area under the curve, and I might want to use these rectangles to help me estimate what that area is. And this is known as the left-hand rectangular approximation method, or LRAM as some textbooks call it. Over here on the right, I'm using right-hand endpoints. Notice the height of these rectangles are based on the right side of the rectangle against the curve. So here we're seeing right-hand rectangles, and I can see all this little extra area that I'm picking up above my curve. That's going to give me an overestimation, isn't it? This would be known as an upper sum, like we had talked about on that previous screen. This one will have upper sum. This guy over here is going to be lower sum because I'm missing area, because these rectangles are inscribed. And the left-hand point of the rectangle follows the curve rather than the right hand. So I can put in my point, my left-hand point, so when x is 0, I can calculate out I've got a height of 1, and that's what I would base my rectangle on. 1 times 1 would give me an area of 1, wouldn't it? Take these out. So I'd have area of 1. Here I have a width of 1 and a height of 1 1/8. That's going to give me an area of 1 1/8. Here I have width of 1 and a height that calculates out to 1 1/2. So I'm going to have an area of 1 1/2. And then this one, if I plug in 3 into my function right here, I'd have 3 squared 9, 9/8 plus 1/8 gives me 2 1/8. And that would be my area. So I would just have to come through here and add all 4 areas up. Boom, I could get my total sum, which is an estimation. So let's actually do one. So, this is for tomorrow. We're going to work on midpoint and trapezoid method. Here's a midpoint method, and then here's another midpoint method where we broke it up into even more rectangles. You can see we increased it by multiplying by 2. Actually, we're up to 8 rectangles, and that's going to get a little bit closer to the actual area. So one method that we can use to get more accurate is to get more rectangles. So left-hand Riemann sum, here we go. We are looking at the function x squared plus 2. That is what this shape of the curve looks like. And we're going to calculate the area under the curve from 0 to 3. So I'm going to be focusing on just from 0 to 3 here under the curve. Now, what we're going to do is, first off, let's figure out how wide each of these rectangles will be. And we're going to call this delta x, which will be our width of our rectangle. So delta x in this case is going to turn out to be b minus a. Well, what is b? B is this endpoint on the right. A is the lower endpoint of the interval that we're interested in calculating area for. So I'm going to say that delta x is equal to 3 minus 0 for a divided by n, and n will represent the number of rectangles or sub-intervals that we're interested in. So we are going to conveniently break this down into 3, which will give us a width of 1. Now we could have broken up into 6 rectangles, and then I would have had, width of 1/2 and make my calculations a little bit more difficult, but also a lot more accurate. So there's a give and take going on there. I'm just going to undo that because we're going to stick with our 3 subintervals with widths of 1. Now, let's go and sketch these rectangles. What I want to do is I want to follow the left-hand method. So I'm going to plot out my left endpoint that's on the curve and draw in my rectangle. I will be calculating the area right in there. Next interval will be at 1, and its height looks like it's at 3. So we'll pick up the area from that rectangle as well. At 2, I'm going to plot my intersection where it intersects the curve. That's a height of 6, and that will give us this last rectangle. We now have 3 sub-intervals or 3 rectangles to add up. I think you probably could look over there very easily and know what this is going to sum to, but I want to get across the idea. The sum is going to be equal to the width of the interval multiplied by the height of the interval. So in my first one, I'd have my x sub 1 value. In this case is 0. So I would take delta x, which is 1, and multiply it by f of 0 in this case. Next, I would take a delta x and multiply it by my second rectangle, f of x sub 2. And in our case, we have a width of 1, and our f value will be calculated at 1. Added with our final third subinterval, which would have the width delta x, multiplied by f of x sub 3. And for our particular case here, f sub 3 looks like a height of 2. So I need to know what f of 2 is equal to. Basically, what we've designed here is width times length of the rectangle, or width times height, however you want to think of it. So conveniently, this formula, if I look back to this first line, I could say delta x is in common to them all. I could factor that out, and then it's going to be f of 0 plus f of 1 plus my height at f of 2. And I'm just going to do a quick little t-chart over here so you can see where these numbers are going to come from, x and f of x, or our y value. X, I need to evaluate 0, I need to evaluate 1, and I also need to evaluate that final left-hand endpoint 2. So f of 0, I'd have 0 squared plus 2, since that's our function. That would give me the height of 2. Makes sense right there, boom. 1 squared is 1, add 2 gives me a height of 3. 2 squared is 4. 4 plus 2 is 6, and that was that final height there. So now I can say my sum is equal to delta x, which is a width of 1, multiplied by the each rectangle's individual height. Kind of a quicker method to do it, and I'd have 1 times 511. So that didn't look very good. Sum equals 11 units squared. I'm not on the smartboard, as you can tell. I'm writing from a little tablet, and it's not quite as neat. So my sum is 11 units squared. This is a lower sum because my rectangles are inscribed. The left-hand endpoint follows under the curve, and therefore we have lower sum. Let's do the next one. Same exact function. We're going to take a look and compare x squared plus 2 on the same interval from 0 to 3 using the same sum interval. So there's our n value. This is our a value. This is our b value. And we're going to do a right-hand Riemann sum. So we can calculate, the width of our delta x, the width of the rectangle. 3 minus 0 for a. And intervals, we're going to do 3 rectangles, so we're going to have widths of 1 just like last time. Let's sketch in those rectangles. This time, we're going to move over to the right side, and that means our first rectangle will start with, let's change colors. Our first rectangle will start at a height then of 3, following the right hand. 2 is my right interval location. It has a height of 6. And finally, 3 will correspond to the right side of our third subinterval. So we would have the area under the red rectangle. You can see that this is going to be an upper sum amount because we have circumscribed rectangles. Okay, let's do our calculation. The sum is equal to delta x times f of, I'm doing right hand, so I need f of 1 plus f of 2 plus f of 3. 3 is the only one I haven't calculated yet. And if I just did a quick little f of x table, plug in 3. 3 squared is 9. 9 plus 2 gives me a height of 11. Okay, so our sum is going to be delta x has a width of 1. F of 1 is 3. F of 2 is 6. And f of 3 has a height of 11. 3 plus 6 is 9. 9 plus 11 is 20. 20 times 1 stays 20. Well, this one's going to be overestimating, obviously, at 20 square units. So that is the right-hand Riemann sum method. It overestimated for us because we had an increasing function which forced our rectangles to be circumscribed. Excellent. So what you have for homework tonight comes from the textbook. It's on section 4.2. Sorry, I didn't put a page number down, but I do have a document that you can print and work these same problems. If you need to use your book, it looks like it's on page 267. Okay, so page 267 is where this is coming from. You're going to be doing an upper and a lower sum. So for this increasing function on 23, an upper sum will follow a right-hand rectangular method, won't it? Oh, that was way off. Because I'm going to overestimate my area with an upper sum. So those are all going to be right hands. The lower sum following my left hand, so I'll be using f of 0, f of 1, f of 2, f of 3 right there. Kind of sketching these in a little bit. So there's my 4 rectangles. And it said just use rectangles of width 1, and that's what will give us an n value at 4 then on this. So calculate out your delta x. I know it's easy, but I would prefer you to actually go through the motion so you know where your calculations are coming from. On 27, they once again want an upper and a lower sum. This is an increasing function. It will be much like 23 and the ones we practiced in notes. And then they want you to break this up into 4 equal rectangles. So you're going to have an interval from 1 to 0 divided by 4, and that's going to be your delta x on that one. This one looks like you're breaking it up into 5 subintervals, so your n value is going to be 5, and once again you're playing from 1 to 0, so calculate out your delta x for that and what that implies for upper and lower sum height levels and stuff. Very good. Hope you have a good day.